Like nimeweka hadi
Please, let's proceed. Please kindly mute your mic if you are not part of this.
Washamba.
Imagine huku normally
skinny jeans from only
lakini
$5.
ikienda sana inakaanga one day haijaipitisha more
Like
than
free hardware and
like,
reinforcements. The only denim to choose.
anyways. Utanitumia tu.
So the second type of relation, symmetric.
Sasa. Aki asante. Na alafu niulize.
So relation
like kwa news sasa.
On a set A. Please, let's come back to class. Kindly.
Kuna kitu najiuliza.
Hey, can you viulize?
Lakini wako na 10 billion ya kusupport.
Omera, come back to class. Stop storytelling.
Watoto hapo wanachojinga.
So relation R on a set A.
Akiwa. Anyway, ni sawa.
Who is this girl?
Unaona hizo pesa watu walikuwa nalipa za NHIF. Ama imekuwa triple na shilingi.
Kataloa kwa group kwa nini? Kwa class.
Pesa mtu alikuwa anakata kwa mshahara imekuwa thrice what you are being cut. Like normal
Mute the
Wesi utoke atolemo.
Nini na wewe? Nimesema atoke anapiga kelele.
Mpige
we ishia bana.
Who is this?
Please, let's come back. Let's come back to class. Kindly.
Kindly,
please. Those who are speaking on phone.
So bye.
Mwalimu, let's continue.
So symmetric relation is the next type of relation under our discussion. So relation R on a set A is said to be symmetric if pair X, Y is in R, means the pair YX is also in R for all for elements X, Y in A. Let me give another definition, then actually I can make more clarification on this. So antisymmetric. A relation R on a set A is said to be antisymmetric if XY being in R and YX being in R implies that X equals to Y for all X and Y in A. Please write those definitions, then I need to make some clarification so that before we give an example to clearly see the difference between the two types of relations, symmetric and antisymmetric, and in terms of how we are defining it. So every term in the definition actually matters to give the distinction.
Yeah. Amegira vila jamani hili.
So we are saying that a relation R on a set A is said to be symmetric if we have a pair XY in relation R, then it must lead you to a pair YX in the same relation R. And remember here, the condition is that for any pair, for any two numbers, X and Y in A, they need not to be all pairs in all numbers in A. But what matters is that once you see an element X, Y in R, then it must lead you to an element Y, X in the same R for any two elements in the set R. So note the difference from the previous definition, whereby the previous definition required all the elements of A to be used to create elements of the form X, X. But here for symmetric, we look for one, what we check for is that once you see an X, Y, then go and look for Y, X in the same relation. If you can find, if you can satisfy all that property for all the elements within the relation R, then R will be called symmetric. And it need not to be for all elements of the set A. It's what dictates the classification as either symmetric or not symmetric is that you have seen an X, Y, then look for Y, X for those two numbers. If that's the case, then the relation will be called symmetric. And remember that that relationship need not to be for all elements of set A. It just need to be taken two at a time. If they satisfy that condition, then the relation will be called symmetric. And then antisymmetric, if a relation R is defined on a set A, then we say R is antisymmetric if you have the pair XY in R, and at the same time you have the pair Y, X in R. That can only be possibility. That possibility is only possible whenever X is equals to Y. And remember, here we are saying that if you do the interchanging between the position of X and the position of Y, then it only turns out that for that thing to happen, then X and Y must be the same numbers. But if you have an X, Y, and also in the same relation we have a Y, X, which are different numbers, X and Y are different, then that relation doesn't qualify to be called antisymmetric. And before we go to the previous example to classify which ones are symmetric and asymmetric, let it be noted that the term symmetric and asymmetric. Please, I beg you to please be attentive. Be attentive, because if you're not very careful, you will be confused by these terms. So kindly be attentive and listen so that you get the distinction properly. If you don't pay a lot of attention, you may have trouble to do the classification. So remain attentive kindly. So the term symmetric and antisymmetric are not opposites. So in the relation, can have both of these properties, or may lack both of them. That's simply to say that when a relation is symmetric, doesn't mean that it can't be antisymmetric. And when it is not symmetric, does not mean that it must be antisymmetric. So they are totally different. Sometimes even the two conditions can be satisfied for the same relation, and sometimes the same relation can actually lack to have all the two properties. So I would like us to do the classification of the previous example from R1 to R6 as to whether which ones of them are symmetric and which ones of them are antisymmetric. So because I'm the only one who is allowed to be lazy, I'll not rewrite them. I'll just go back and want us to discuss. So probably create time and rewrite these examples in the spaces that you have written symmetric and antisymmetric. Then I want us to do the classification one at a time. Or maybe not really, let me not box you to one corner. From the definition, I would like anyone to classify any of the relation that you think satisfy the condition of symmetric and why you think that the relation is truly symmetric from the definition. From R1 to R6, which of these form a symmetric relation? And why do you think so? So who can actually, in simple terms, who can tell us if we want to do the classification as symmetric, what should we look for? What must we look for us to say that a relation is symmetric from the definition? From the definition, what should we look for us to classify a relation as symmetric?
So we should check the XY.
XY?
XY should
Correct.
be implied with the YX.
YX. Yeah, that's really what you do. That we identify an X, Y, and then show that when you have an X, Y, there is a Y, X in the same relation.
Yeah.
If we do that comparison for all the elements of the relation and we see that condition being satisfied, then we classify the relation as symmetric. So maybe let's go to R1. So the first pair 1, 1 doesn't matter because when you change it, the same element. So that one has no problem. So the next element is 1, 2. So when you see 1, 2, what are we expected also to have in the same relation?
2, 1.
2, 1, and it is there. Okay? Yeah. And then 2, 2, there's no problem because when you change the role of X and the role of Y will be the same element. So there's no problem with the same element, 2, 2. And then here we have 3, 4. What must we look for in the same relation?
4, 3.
Is it there?
4, 3.
No.
No.
So there is 3, 4, but 4, 3 is missing. So therefore R1 is?
Yes. It is not symmetric.
Yes, so R1 is not symmetric. So this one is not symmetric.
Yes.
It's not symmetric because of that actually. If you just find one counterexample, it's enough actually to make you to actually justify your answer of why you are saying that it's not symmetric. So we are saying that R1 is not symmetric since, for example, an element 3, 4 is in R1, but 4, 3 is not in R1. So therefore, that one alone qualifies R1 to be called not symmetric. Please remember, when you say not symmetric, does not mean antisymmetric. Just say not symmetric and you keep quiet, and then you give the explanation. Because the two don't mean opposite. The two are not opposites. Good. So then R2, is it symmetric or is not unsymmetric? So we go that element, we just do element term by term, and then we'll be element by element, then we'll be able to do the classification, whether it qualifies the definition or not. So 1, there's no problem because when you interchange the same element, so it's still that that property is implied in itself. Then there's a 1, 2. You expect to have
2, 1.
1. Is it there?
Yes.
Yes.
So what do we conclude?
It's
It is
symmetric.
symmetric.
Yeah. So therefore, this one R2 is symmetric because all the properties of the symmetric relation are satisfied. Remember, 1, 1 and 1, 1 itself actually is implied. So it's actually itself. So this condition is satisfied whenever the first element and the second element are the same numbers. When you interchange, you get the same element. And remember, when you were discussing about sets from the introductory, we said that repeating an element in a set does not create a new element. So it's like we still can rewrite another 1, 1 just to justify that we are interchanging the roles of x and y, the same thing. R3, 1, 1 has no problem. 1, 2, we expect to have
2, 1.
2,
1. Is it there?
Yes.
Yeah, so it's there. And then 1, 4. Expect to have. This is 1, 4. So what are we expected to also have?
4, 1.
4, 1, and it's there, okay? 2, 2, there's no problem. 3, 3, there's no problem. 4, 4, there's no problem. So is it symmetric?
Yes, it is. Yeah. 1, 1, 1.
Is it symmetric?
Yes.
Yes.
Yeah, symmetric because all those properties are satisfied. So this is also symmetric.
Yes.
Yeah. Then R4. This is 2, 1. So what are we expected to have?
1, 2.
Is it there?
No.
So therefore, this is not symmetric. Once you just have 1, it's enough. Not symmetric.
Yes.
Not symmetric, and you can actually give. You can actually justify your answer by actually giving that reason that it's not symmetric since we have 2, 1 is in this relation R4, but 1, 2 is not
1,
in R4. Good. And then R5. So we have 1, 1. So there's no problem when the elements are the same for the first and second. 1, 2.
There's no 2, 1.
There's no 2, 1. So is it symmetric?
No.
So it's not symmetric. Not symmetric because you can actually give the same reason. Not symmetric because, for example, there's an element 1, 2, and 2, 1 is missing, so it doesn't qualify. R6.
Not symmetric.
What makes it not be symmetric?
Since there is a set of 3, 4, and there's no 4, 3.
Yeah, there's no 4, 3. So assuming we had a 4, 3, then R6 will be symmetric, okay?
Yeah.
Yeah, not symmetric since this element 3, 4 is in R6, but 4, 3 is not in R6. Correct. Good. So we have successfully done the classification for R1 to R6 in terms of symmetric. Now the next thing I want us to do is to use the same relations and now classify which ones are unsymmetric and which ones are not. So I want us to use the same relations to classify them as unsymmetric or not unsymmetric. And so when you are defining unsymmetric, what are we supposed to check for?
So we're supposed to check y.
X, y, y, x.
Remember there are two ways.
And
There are two ways
x
of
is
actually
equals to
responding to a
y.
problem. There are two ways. If you can find a way of actually justifying that it can't be, then it's still okay. Or if you can find a way of saying that it is still another way of actually defending your answer. So we say that relation R is antisymmetric if
XY.
if XY is in R and
Y implies
YX is in R, then
Implies that XY
Equals to Y.
X equals to Y.
X equals to Y, correct. So then now the easiest way to classify the relation in terms of symmetric, antisymmetric, or not antisymmetric is simply check. So this is the simplest test. So find a pair, say X, Y, with X not equals to Y, such that X, Y and Y, X are both
equal
in the relation. And so if this is the case, is it antisymmetric or is not antisymmetric? If now we find a pair X, Y with X not equals to Y, such that XY and also YX are in that relation, do we say that this relation is antisymmetric or is not antisymmetric? Will it be antisymmetric or not antisymmetric? According to the definition.
No. XY is
Now
not.
this disqualifies the relation being antisymmetric, okay? So the easiest way to start with now, for example, let's go to R1. Let's go to R1 and see. I remember those pairs which have same elements have no problem because they satisfy the condition for antisymmetric. So they are like 1, 1, 2, 2, 3, 3, 4, 4 doesn't. Those are actually the things that we look for if the relation is going to be antisymmetric. But then if we are able to say that there is an X, Y and a Y, X, and those two numbers are different, then the relation is not antisymmetric. So let's see. 1, 1, there's no problem. 1, 2. Is there a 2, 1?
Yes.
So is it antisymmetric or not antisymmetric?
Not antisymmetric.
Not antisymmetric. Because we remember we are having YX interchanging the role with Y, interchanging with XY, Y interchanging, so having YX, so that the two numbers, X and Y, they interchange the roles, and all those two elements are within the same relation, and the numbers are different. So therefore, that one alone disqualifies the relation from being antisymmetric. So therefore, R1 is not, this one is not antisymmetric. And then R2. So when we have 1, 1, there's no problem here. Here you have 1, 2. Is there a 2, 1?
Yes.
Yes.
So is it antisymmetric or not antisymmetric?
Not antisymmetric.
Not antisymmetric because the interchanging of the roles of X and Y, both elements are there and the numbers are different. So this one is not antisymmetric. R3.
What's the difference between the two of them?
This one is not, because also we have 1, 2, and 2, 1. Both of them are included here, and they are different numbers. So this one is not. R4. Let's now start one by one. There is a 2, 1. Is there a 1, 2?
No.
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 So we really can now really say that not antisymmetric, because actually there's no x comma y and y comma x in the same relation. So let's go to the next one. 3 1. Is there 1 3?
No.
No.
And then 3 2.
No.
Is there a 2 3?
No.
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 4 1. Is there a 1 4?
No.
No.
4 2. Is there a 2 4?
No.
No.
4 3. Is there a 3 4?
No.
No. So there what the verdict?
Symmetric. Antisymmetric.
This one is now antisymmetric.
Yeah.
Antisymmetric.
Wow.
Then for the case of 1 1, there's usually no problem because x equals to 1. So there's no worry. And next element is 1 2. Is there a 2 1?
No.
No. So we go to the next. 1 3. Is there a 3 1?
Hell
No.
no.
1 4. Is there a 4 1?
No.
No. 2 2. There's no problem. 2 3. Is there a 3 2?
No.
No. 2 4. Is there a 4 2?
No.
No. 3 3. There's no problem. 3 4. Is there a 4 3?
No.
So 4 4. There's no problem. So what the verdict? So R5 is antisymmetric, correct. Then R6, there is a 3 4. Is there a 4 3?
No.
Oh, so then what the verdict? What the verdict now?
Antisymmetric.
And this antisymmetric. Then let's go to that. You remember what we used to say, that a relation R where those who are making noise, can you kindly concentrate on? If you are not for this one, you actually go out.
Yes.
Contains.
Can you give me the elements of this relation that we previously defined, where we had A divides B? What were the elements of this relation?
1 1.
1 1.
1 2.
1 2.
1 2. 1 3.
1 3.
1 3.
1 4.
1 4. 2 2.
2 4.
2 4.
3 3.
3 3.
4 4.
4 4. So this is what we had as the elements of the relation R, where the condition is that A divides B. Now, I want us to check whether this is symmetric or unsymmetric. So is R symmetric? And is R antisymmetric?
One option.
So can you check for me whether R is symmetric? And once you have done that one, also check for me whether R is antisymmetric. Let's start with the first one. Can we say that R is symmetric? Yes or no?
No.
Why?
No.
What makes it not be symmetric?
Since there is 1 in R, but there is no 2 1.
Correct. So this one is not symmetric. E.g. 1 2 is in this relation, but 2 1 is not in this relation. Good. So that is the reason. So R, the divide relation is not symmetric. Now, is it antisymmetric?
Yes.
It is antisymmetric. So this one is antisymmetric. Because there is no x comma y and y comma x, which implies that x and y are different numbers. So therefore R is antisymmetric. So the other definition, that's number 4. There's what we call transitive.
Excuse, excuse, I have a question.
Yes.
Can a relation be both symmetric and antisymmetric?
No.
Yes, it can.
An
For example, if we have this, that's a good question. Like if I have a relation, if I have, let me delete this one. Like if I define a relation R11, 1, 2, 2, 2, 3, 3, and say 4, 4. Do you think that this is symmetric? Do you agree that this relation is symmetric?
Yes.
Yeah, and it's also antisymmetric.
Yes.
Why?
Yeah.
Do you think that R is also antisymmetric?
Yes.
So this one is both symmetric and antisymmetric.
Thank you for example.
Okay, fine, good. So transitive.
I also have a question.
Wanamtauliza maswali wengi kumaliza nini?
Yeah, I have a question Banaika.
Sasa nimeelewa hapo.
What the question?
When we are giving the answer, is it a must we say the reason why is it
Yes.
not symmetric?
Yes. When you are giving your answer, you have to give a reason.
Okay.
When you are saying that it's symmetric or not antisymmetric, it's not antisymmetric, then you have to give a reason.
Thank you.
Okay. So a relation R on a set A is said to be transitive if whenever an element XY is in R and YZ is in R, then X Z must be in R for all these three numbers, X, Y, and Z. So relation R is said to be relation R on A is said to be transitive if we have these two elements, X, Y, and Y, Z in R. Then you must have an element X, Z in R for all X, Y, Z in A. Before I give an example there, then let me also give another definition.
Mwalimu, hiyo ni YZ?
Yes. This first one is XY in R. Next one is YZ in R. And then this XZ for all XYZ in A. I don't know if I've responded to your question.
Excuse.
Yes.
You have said that, okay, the relation R on a set A is said to be transitive whenever XY is on R.
Is in R.
The one is written there, is it Z, Y, Z, or what?
Head.
Okay, I will know that you are senior people now. When we started this course, this is a sign for an element or belongs to. So this is what I've written here. This belongs to this belongs to sign or member of. So XY belongs to R, or is a member of R, or is an element in R.
Yes.
So this sign here is this visual belongingness sign.
Okay.
Is this clear now?
Yeah, it is clear.
Oh, okay, fine, good. So there's also what we call an equivalence relation. So a relation R on a set A.
Example number 4.
Yes, we are. I mean, we'll demonstrate. We'll do the same thing on the R1 to R6. So don't worry. Just like then we'll classify those R1 to R6 as transitive or not. Okay.
Yes.
Yeah. So an equivalence relation. A relation R on a set A is said to be equivalent to be an equivalence relation if it is reflexive, symmetric, and transitive. The equivalence relation should actually satisfy 3 conditions. First condition is reflexive, second condition is symmetric, and third condition is transitive. And then lastly, partial order.
Is the last.
Yeah, this is the last one. This is the last one. Once we explain the transitive, then you should be able now to do the rest of the thing. We stop. So our relation R on a set A is said to be a partial order if it is reflexive, antisymmetric, and transitive. So partial ordering requires 3 conditions to be satisfied: reflexive, antisymmetric, and transitive. So then now when you explain the interpretation of the classification of a relation as transitive, then the rest of the terms should actually be obvious to be able to write the definition. Then we still go back to our R1 to R6. We want to classify them as either transitive or not transitive. So let's go back to our R1 to R6. and classify them as either transitive or non-transitive. So the key thing is that how do you do the classification? What must you check? What should we check for us to classify a relation as transitive or not transitive?
Transitive.
What is the key component for you to do the classification in the transitive test?
X.
So what we need to, so this actually, this is a key thing that you need to have. For transitive, this is what you need to have, that you see an X, comma Y, and you see a Y, comma Z, then this should tell you that you need to see what?
X, comma Z.
Z, yeah. So like there are three numbers. There are three numbers, X, Y, and Z. So if X is related to Y, X is related to Y, and then Y is related to Z, then this should lead you to an element which relates X and Z. Yeah, so that's really what you do. There are three numbers in that called the relationship. So so 1, 1. There's 1, 1. Let's say R1, whether it is transitive or not. So, okay, is it transitive or not transitive? So you can actually find the easiest way to do the classification is that if you can actually find a direct counterexample, then you actually can easily do the classification. If you can easily see a counterexample that respects the definition of the relation itself. Like you see here. Yes, there is any quick counterexample that makes it either to fail or to be.
I guess it is transitive because we have 1, 2. We have 2, 1.
2, 1, and we have 1, 1.
4, we have 4, 1.
And then is okay. That will be taking care of the first three elements. Are all of them going to respect that?
No.
Like which elements will not respect that definition?
Like
2,
2.
And 3, 4.
No, 2, 2, and 3, 4 cannot be related. Remember, we have to relate X, Y, Y, Z, so to have X, Z. So it's like the first bracket has an element Y. Then the other bracket you would be doing comparison with should start with a Y.
Yes. Yeah.
So that's how it goes. That once you have the first bracket, the first pair, then the last element in the first pair should be the starting element in the pair you want to compare with.
Okay.
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 It is 2 is called.
Imekubalika. Understood.
Okay, so then now tell
R1
me,
is
so
not transitive.
do all of them satisfy that condition? Like for the first three, they will be actually be okay. But are all of them?
No.
Like even if you say 1, 1, and then 1, 2. So is there a 1, 2 in this? Because like you say, this is if I call this as my X, this is my Y, this is my Y, this is my Z.
Yeah.
So you see, Y ending, the number ending the first pair is the same as the starting number in this other pair. So actually, they should actually be, should help us to define the transitivity of the relation. So do we have a 1, 2 in this relation is there, so there's no problem. But then now, 3, 4 and 4, 3, do they obey that structure?
No.
What makes it to fail?
We don't have
There's no 3-1.
There is no 3, 1. Okay.
3, 1 and
yeah, 3, 1 is lacking because you see, this last number here is matching with this first number, this other pair. But so if that is the case, then we expect these two numbers to be related. So an element 3, 1 should be within R1 for this thing to be transitive. So therefore, this one is not transitive. Since 3, 4, then 4, 1 are in R1, but 3, 1, 3, 1 is not in R1. So that's the reason for that answer. That we have the first two pairs obeying the first part of the definition, but then the first number in the first pair is not related to the last number in the second pair. Now, is R2 transitive or not transitive?
Transitive.
R2 is transitive because actually all that conditions will be obeyed or will be actually be satisfied in that condition, correct? So this is transitive. And then R3?
Not transitive.
In fact, the easiest way is to just to check whether there are two
Not
pairs which will actually
transitive.
not satisfy the definition, and then you say no. But if you can't find, then it is.
Yes, but
I have a question. Excuse me, sir.
Yes.
I have a question. R2.
Yes.
The first one is in form of X, Y, and the second one is of YZ.
Okay, yeah. So let's see. Okay, so what 1 X Y?
Yes.
Y.
And this is
YZ.
YZ.
In form of
YZ.
YZ.
then XZ should be 1, 2, but the third one is 2, 1.
No,
Eh?
it's not supposed to be like that. No, a mistake.
But we have 2 in R2. We have 1.
Okay, yeah, actually, you have a point, is true. This one is not transitive. You see, these two elements here, or we have 2, 1, and we have 1, 2, 1, 2. So this doesn't matter the order of how we are writing them. So you see, also here, if this is our X, these are Y, these are Y, these are Z. Then you see, we need to have a 2, 2.
2, 2.
Yeah.
Which is lacking, okay? So the key thing is that when you rearrange this element and this element here, doesn't change the structure of R2, but this 2, 1 and 1, 2 obeys X, Y, X, Y, and YZ. So XZ 2, 2 elements should actually be within this relation.
It's not going through.
Excuse.
It's not going through, sir. There's a wall.
Nafikiria R2 ni transitive.
The class is over. Mwalimu. Olo. That bwana. Imeisha bao.
Disappeared.
What is not happening?
I think he's set on time. Maybe he has to leave that time.
I think the deck has gone. Yeah. Thank you for attending the lesson.
Acha ujinga.
Okay, let's call it a day. Let's call it a
Ujinga
day.
mwenye kufikiria life na
Bana, huyo manzi anaongea sana.
Edgar.
Where's Zimo?
Lol, Edgar. What are you saying?
Forever.
Let's call it a day.
Sorry about that small network glitch. So we are saying that hello. I hope you can still see my screen.
Yes.
Yeah, good.
Yes.
So I was saying that the relation R2 is not transitive because of what actually has been said, that an element 2,1 and 1,2 obeys the structure x, y and y, z, but then x, z will not be there. 2,2 is not in R2. So for R2 to be transitive, then we need to add an element 2,2. So for that condition to be satisfied. So therefore relation R2 is not transitive.
Yes.
Then R3. So R2 is not transitive. Then the reason is that this 2,1 and 1,2 are in R2, but the element 2,2 is not in R2. Then R3, is it transitive or not transitive?
Mwalimu.
Yes. Yes, ask.
Yeah, because you have as the element of R.
R2 bwana.
Not transitive of 2,2 and 3,3.
We are not.
So remember order. We started by saying that order does not matter when you are listing elements of a set. Order does not matter when you are listing elements of a set. And remember, for the test of transitivity, you need actually to have two pairs such that the first element, the second element in the first pair agrees with the first element in the other pair. So once you have that one, then you'll have the relation x, y, and we have the association x, y, and y, z. So which dictates that for it to be transitive, then you need to have an x related to z, which is not being satisfied by this R2 for the last two elements as written.
The first element.
Can you get it clear? We are not understanding.
Kabisa.
Hebu fanyeni aje? Kwa hii R2 hiyo xy equal hiyo 1 2. Alafu yz equal 2 1. Sasa xz equal 1 1.
Wewe
Even.
Kwani guys xz yetu ni gani? Si inafaa kuwa hiyo 1 2. Na siko under the elements of R. Hiyo 1 2.
Kwani again
Continue in our next process. We are exhausted.
Time is up.
sasa yeye mtu ameweka kingoma ya Kisomali. Shida ya watu ni wa nini? Ni Juleka amepotea.
Hivi nataki kuona.
Hiyo si Kisomali. Hiyo si
Mbaya kali. This girl is just Maya Khalifa. I didn't really go over
Stephen, tumeona kwenye
Ito sura hapo.
Inyo kaje koro lero go mu face de kayo.
Ito sura hapo.
Nilijua tu ameuma nje.
Hiyo Steve no kumbe endo kuosha vyombo huko India.
Siwezi kuficha sura kama umejiaminia. Nini mbaya na huyu mwanzi man?
Hai, nini yao unaficha?
Unaficha vio.
Suleiman Mohammed.
What do you want to say?
Gitao, hi.
Yeah.
Let's call it a day.
We call it a day. I don't know why you're having the day.
Your wife.
mingi sana.
Let's call it a day. No, bro, let your chaya, bro.
Sasa toto. Mambo.
Not this guy again. We zima hiyo kitu. We mrazi.
Mlikuwa mnasoma nini?
Okay, sorry for that disruption. So we were discussing about R3. Is R3 transitive or not transitive?
Mwalimu, we are not done.
Hello. Is R3 transitive or not transitive?
Not transitive.
Why? Why is it not transitive?
Okay.
2, 2 and 3, 3.
So 2, 2 and
3, 3.
3, 3.
So 2, 2 and 3, 3 cannot be related. You can't remember. We need to relate x, y, y, z, and then have x, z. So 2, 2 and 3, 3 can't be related. Those two pairs.
Yeah.
So that cannot be a reason. That cannot be a reason as to say that if the relation is not transitive because of 2, 2 and 3, 3. A reason can be like what you're saying in R2, that we have a 2, 1 and we have a 1, 2, but then 2, 2 is not in R2. So that this last element here and the first element here are matching.
Mwalimu, in that one, that R2.
R3?
R2, if you use 1, 2 as XY and 2, 1 as YZ.
If you use 1?
If you use 1, 2 as XY.
2, 2?
If you use 1, 2 as XY.
1, 2? Yes.
As XY.
XY.
And 2, 1 as YZ.
2, 1 as YZ. Yes. Yeah, there's 1, 1 there. 1, 1 is there. There's no problem.
Okay.
Yeah, there's no problem. But remember, the thing is that you need to check all possible pairs which actually satisfy that condition. But if you find there are two elements or two pairs which don't satisfy the condition, then that's what disqualifies the relation from being transitive. Because if you find an x related to y and y related to x in the same relation, then it calls for having an x being related to z. If it's not there, then actually it doesn't satisfy the definition of transitive. So if we can find one counter example, then that's enough to say that this relation is not transitive. So by having 1, 2, and 2, 1, giving 1, 1, which is there, does not mean that now that is enough. If we have one that satisfies x, y, y, z that doesn't satisfy x, z, then this relation is not transitive.
Yes.
So R3, is it transitive or not transitive?
It is not.
What is the reason? If you say it's not, then produce two pairs which satisfy x, y, y, z, and there's no x, z.
2, 3.
2 and 3, 3.
That's the easiest way to say that now. You are for you to comfortably
2, 1,
say what
3,
you're
3.
saying. That yes.
2, 1, 3, 3.
2
and 3, 3 cannot be related.
2, 1, and 3, 3 cannot be.
Remember, pairs which have the same x and y, they are answers on their own. Because when you have 3, 3, you can add there 3, 3. Doesn't cause any problem, and you produce the same pair. So pairs with same x and y, there's no problem. All the conditions are satisfied within themselves. For 2, 2, 3, 3, 1, 1, there's no problem. It's like just you duplicate another 1, 1, or another 2, 2, another 3, 3, which will be satisfying the same condition. So for that one, there's no problem. When we have same x and same y. Are you able to find any pair that will be disobeying that condition? That there's an xy and yz, and there's no xz in R3?
No.
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 You are sure?
It is
Transitive, yes, it is transitive.
that is, yes.
Transitive.
Okay, this is the easiest way. This is the easiest way to check the transitivity. So remember, we have an x related to y. So it's very easy to check whether there are two pairs that doesn't satisfy that property for you to disqualify. So we need x to be related to y, and then we have y related to z. So we need to have x related to z. Now let's see. We have numbers 1, 2, 3, and 4 as where the set on which these relations R1 to R6 were defined was having elements 1, 2, 3, and 4. So y, the middle number, this y is actually what is common to these two pairs. So let's check in these random pairs that forms the elements of R3. Let's check each of these elements are the second element in each pair and see whether we can find another pair with the same element being its starting element. So this is what I mean. Let's scan through and see. Like in this bracket, I have 1 as my second element. This I have 1 as my second element, and this I have 1 as second element. Then, for us to relate these brackets which have 1 as their second element, this pair, and this other pair, I expect my other pair to start with also the same element 1 for us to relate it to have this relationship. So the other pairs that starts with 1 I have this. I have this. So those are the two pairs that starts with 1. So which means that I can have 1, 1 can be related to 1, 2. 1, 1 can be related to 1, 4. And the other thing is 2, 1 can be related to 1, 2. And then 2, 1 can be related to 1, 4. And then the other possibility is that 4, 1 can be related to 1, 2. And then also 4, 1 can be related to 1, 4. Are you seeing that?
No.
That we check for a second element in the pairs forming the relation and try to see which other pairs have that number as the starting number. So I started by saying that the element 1 in this first pair is the second element in this pair. And then 1 is the second element here. 1 is the second element here. So for these for these 3 brackets, or these 3 pairs, for us to relate it to get the aspect of condition to be satisfied for transitivity, then I need to relate to pairs which now are starting with 1 as the element of the starting with 1 as the first element. So I have 1, 2, I have 1, 4. Those are the only pairs that starts with 1. So I can always relate 1, 1 to 1, 2, 1, 1 to 1, 4. So that this forms my X, my Y, my Z. And then similarly, I can have 2, 1 related to 1, 2, or 2, 1 related to 1, 4. And then 4, 1 related to 1, 2, 4, 1 related to 1, 4. And let's see whether all these possibilities for element 1 satisfy the conditions for transitivity. So when I have 1, 1 and 1, 2, I expect to have if this is my 2 pairs, which element do am I expected to have in the same relation?
1, 2.
1, 2. This first element and the second element. 1, 2. Is 1, 2 in this R3?
Yeah.
Can you see an element 1, 2 in R3?
Yes.
It is there.
Yeah.
So there's no problem for that, okay?
Mm.
Then
Yes.
1, 1 and 1, 4. What am I expected also to have in R3?
1, 4.
1, 4.
1, 4. Is
1,
it there?
4.
Yes.
Yes.
So it's there. There's no problem. And then 2, 1 and 1, 2. What am I expected to have?
2, 2.
2, 2. Is 2, 2 there?
Yeah.
Yes.
So 2, 2 is there. And then 2, 1 and 1, 4. I'm expected to have?
2, 4.
2, 4.
2, 4. Is 2, 4 in that R3?
No.
So then what's the verdict?
Is not.
Wait.
Not
Check on you not
R3?
It's not.
R3 is not, because remember 1, 2 can be related to 1, 4. And so expect to have an element 2, 4 in the same R3. So 2, 4 is not here. So therefore, this not being there is enough to tell us that R3 is not transitive. Okay, if we are to go to 4, 1 and 1, 4, 1 and 1, 2, we are expected to have
4, 2.
4, 2. Is there 4, 2?
No.
No.
So that still can also be another reason as to why we are saying that R3 is not transitive. And then 1, 4 and 4, 1 and 1, 4, this will be there. But you see, this 4, 2 and 2, 4 are not in this relation, yet 2, 1 and 1, 4 are there, and 4, 1 and 1, 2 are there. So therefore, R3 is not transitive. R3 is not transitive. Can you check whether R4 is transitive or not? So R3, we are concluding that it's not transitive, and the reason is that element 2, 1 and 1, 4 are in R3, but we are missing 2, 4. Or you can give the reason element 4, 1 and 1, 2 are in R3, but element 4, 2 is lacking in R3. So remember, once you just get one count example, it's enough reason to justify your answer. So check whether R4 is transitive or not.
R4, you have 2, 2, 2, 1. We have
Yeah.
3.
R4
It's transitive.
Is
so R4 check that all those conditions for transitivity will hold at your own free time. So this is transitive. Check that when you check all the conditions for transitivity for all the elements in R4, R4 will be transitive. Similarly, R5 is transitive. And R6 is also transitive. Do you know why we are concluding that R6 is transitive? Maybe before even R6. Do you know why we are saying that R6 is transitive?
No.
No.
What is the definition of transitive?
We say it's whenever X and Y are in R.
So what is the definition of a transitive relation? Remember the definition of transitive, we say that a relation R is transitive if whenever XY is in R and YZ is in R.
And why are we saying R6?
So when we say whenever XY is in R and YZ is in R, then XZ must be in R. For these numbers, X, Y, Z in R.
Yeah.
So respect every term in the definition. So we are saying that whenever X, Y is in R and Y, Z is in R. But remember here we just have 3 and 4 as one pair. So then this the element which is in R6 or the definition of R6, there is no rule that is actually disobeyed to say that X, Y, and YZ are in R, but then XZ is not in R. So trivially, so when you have only one element in the relation, then it is transitive by default because it doesn't disobey the condition that you need to have two pairs, X, Y, and YZ, to be in the same relation to force an XZ to be in the same relation. So when we say whenever, this whenever part, if there are no 3 elements to compare with, then it's actually trivially obeyed by default. So R6 is transitive. So then now get more examples on the same and get examples of relations which are equivalent and partial order from the definition. Now that you know what reflexive is, symmetric and antisymmetric. So have a good day.
You too.
Good.
Oh my God.
Hey, Jesus Christ.
You
guys,
too.
Hey,